Our topic for today is stream flow. We know that stream flow, we will ask somebody to read this one for us. Will you please have it read? Maika? Maika?
Sir, hindi pa po.
Pakibasa.
Di pa po, sir, open yung
Yan.
PowerPoint.
Bukas na.
Okay na.
Stream flow, representing the run-off phase of the hydrologic cycle, is the most important basic data for hydrologic studies. It was seen in the previous chapters that precipitation, evaporation, and evapotranspiration are all difficult to measure exactly, and the presently adopted methods have severe limitations. In contrast, the measurement of stream flow is amenable to fairly accurate assessment. Interestingly, stream flow is the only part of the hydrologic cycle that can be measured accurately. A stream can be defined as a flow channel into which the surface runoff from a specified basin drains. Generally, there is considerable exchange of water between a stream and the underground water. Stream flow is measured in units of discharge, cubic meter per second, occurring at a specified time and constitutes historical data. The measurement of discharge in a stream forms an important branch of hydrometry, the science and practice of water measurement.
Okay, please proceed.
Stream flow measurement techniques can be broadly classified into two categories, as one direct determination and H indirect I direct determination and H indirect determination. Under each category, there are a host of methods. The important ones are listed below. Direct determination of stream discharge. A. Area velocity methods. B. Dilution techniques. C. Electromagnetic method. And D. Ultrasonic method. Indirect determination of stream flow. A. Hydraulic structures such as weirs, flumes, and gated structures. And B. Slope area method. Barring a few exceptional cases, continuous measurement of stream discharge is very difficult to obtain. As a rule, direct measurement of discharge is a very time-consuming and costly procedure. Hence, a two-step procedure is followed. First, the discharge is given stream is related to the elevation of the water surface stage through a series of careful measurements. In the next step, the stage of the stream is observed routinely in a relatively inexpensive manner, and the discharge is estimated by using the previously determined stage-discharge relationship. The observation of the stage is easy, inexpensive, and if desired, continuous readings can also be obtained. This method of discharge determination of streams is adopted universally.
Mm.
Measurement of stage. The stage of a river is defined as its water surface elevation measured above a datum. This datum can be mean sea level or MSL or any arbitrary datum connected independently to the MSL. Staff gauge. The simplest of stage measurements are made by noting the elevation of the water surface in contact with a fixed graduated staff. The staff is made of a durable material with a low coefficient of expansion with respect to both temperature and moisture. This is fixed rigidly to a structure such as abutment, pier, wall, etc. The staff may be vertical or inclined with clearly and accurately graduated permanent markings. The markings are distinctive, easy to read from a distance, and are similar to those on a surveying staff. Sometimes it may not be possible to read the entire range of water surface elevations of a stream by a single gauge, and in such cases the gauge is built in sections at different locations. Such gauges are called sectional gauges, which is shown in Figure 1. When installing sectional gauges, care must be taken to provide an overlap between various gauges and to refer all the sections to the same common datum.
Okay, so you have there the figure. On the left side, you have the vertical staff gauge, a single gauge, no, anchored in the abutment, while on the right side, the sectional staff gauge, you have a series installed in a line to monitor water level, particularly in case of flood, no? Sectional because maybe the the flood area is high. That's why you need at least three or two staff gates to be installed there in order to determine the depth of water in a river. Okay. Please continue.
Wire gauge. It is a gauge used to measure the water surface elevation from above the surface, such as from a bridge or similar structure. In this, a wire gauge is lowered by a reel to touch the water surface. A mechanical device measures the location of the wheel, which is proportional to the length of the wire paid out. The operating range of this kind of gauge is about 25 meters. Automatic stage recorders. The stage gauge and wire gauge described earlier are manual gauges. While they are simple and inexpensive, they have to be read at frequent intervals to define the variation of stage with time accurately. Automatic stage recorders overcome this basic ob- objection of manual staff gauges and find considerable use in stream flow measurement practice. Two typical automatic stage recorders are described below.
Okay. So that's the automatic gauge recorder. Actually, you have one of like this in Pag-asa, Kamaligan, wherein the depth of water is being measured automatically by means of a float. No, that's how it looks like. Okay. Please proceed.
Float gauge recorder. The float-operated stage recorder is the most common type of automatic stage recorder in use. In this, a float operating is in a steering well is balanced by means of a counterweight over the pulley of a recorder. Displacement of the float due to the rising or lowering of the water surface elevation causes an angular displacement of the pulley and hence of the input shaft of the recorder. Mechanical linkages convert this angular displacement to the linear displacement of a pen to record over a drum driven by clockwork. The pen traverse is continuous with automatic reversing when it reaches the full width of the chart. A clockwork mechanism runs the recorder for a day, week, or fortnight and provides a continuous plot of stage versus time. A good instrument will have a large size float and least friction. Improvements over this basic analog model consist of models that gives digital signals recorded on a punch tape, magnetic tape, or transmit directly onto a central data processing center. To protect the float from debris and to reduce the water surface wave effects on the recording, steering wells are provided in all float-type stage recorder installations. Figure 2 shows a typical steering well installation. Note the intake pipes that communicate with the river and flushing arrangement to flush these intake pipes of the sediment and debris occasionally. The water stage recorder has to be located above the highest water level expected in the stream to prevent it from getting inundated during floods. Further, the instrument must be properly housed in a suitable enclosure to protect it from the weather elements and vandalism. On account of this, the water stage recorder installations prove to be costly in most instances. A water depth recorder is shown in Figure 3.
Okay, so you have there the section of steering well installation. Actually, the different parts, you have the walkway, the flush tank, then the recorder, the manhole, then the float, no? So the float is the one moving at the same time. The depth is being recorded. You have the counterweight here. So as it rises, you can determine the depth of flow in a particular river using this steering well installation. That's how it looks like, the Steven type recorder. Okay, please proceed.
Bubble gauge. In this gauge, compressed air or gas is made to bleed out at a very small rate through an outlet placed at the bottom of the river. A pressure gauge measures the gas pressure, which in turn is equal to the water column above the outlet. A small change in the water surface elevation is felt as a change in pressure from the present value at the pressure gauge, and this in turn is adjusted by a servo mechanism to bring the gas to bleed at the original rate under the new head. The pressure gauge reads the new water depth, which is transmitted to our recorder.
Okay, so seldom we use this in our country, but then for advanced countries, we are using that, especially that maintenance of this type is rather a problem. No? Okay, let's proceed.
Stage data. The stage data is often presented in the form of a plot or stage against chronological time, known as stage hydrograph. In addition to its use in determination of stream discharge, stage data itself is of importance in flood warning and flood protection works.
Okay,
Measurement of velocity. The measurement of velocity is an important aspect of many direct stream flow measurement techniques. A mechanical device called current meter, consisting essentially of a rotating element, is probably the most commonly used instrument for accurate determination of the stream velocity field. Approximate stream velocities can be determined by floats. Current meters, the most commonly used instrument in hydrometry to measure the essentially of a rotating element which rotates due to the reaction of the stream current with an angular velocity proportional to the stream velocity. Historically, Robert Hooke, 1663, invented a propeller-type current meter to measure the distance traversed by a ship. The present-day cup-type instrument and the electrical make and break mechanisms were invented by Henry in 1868. There are two main types of current meters. The first one is the vertical axis meters and second horizontal axis meters.
Okay, the vertical axis meter. Will you please read?
Vertical axis meters. These instruments consist of a series of conical cups mounted around a vertical axis, which is shown in figure 6 and 7. The cups rotate in a horizontal plane and the cam attached to the vertical axis spindle records generated signals proportional to the revolutions of the cup assembly. The Price current meter and Gurley current meter are typical instruments under this category. The normal range of velocities is from 0.15 to 4 meters per second. The accuracy of these instruments is about 1.50% at the threshold value and improves to about 0.30% at speeds in excess of 1 meter per second. Vertical axis instruments have the disadvantage that they cannot be used in situations where there are appreciable vertical components of velocities. For example, the instrument shows a positive velocity when it is lifted vertically in still water.
So in this case, the different parts of this current meter, this is the sounding weight, no? Call this as torpedo. The main purpose is to hold the current meter in place, then the stabilizing fin, the hoist, the support, electrical connections, then this is the cup, the one rotating that will measure the velocity. Now this is immersed in water in order that you can measure the velocity. Okay. Yeah, that is how it looks like. The cup type current meter with sounding weight. Okay, please
Sounding
continue.
weights. Current meters are weighted down by lead weights called sounding weights to enable them to be positioned in a stable manner at the required location in flowing water. These weights are of streamlined shape with a fin in the rear and are connected to the current meter by a hanger bar and pin assemblies. Sounding waves weights come in different sizes and the minimum weight is estimated as W is equals to 50 V bar D, where W is the minimum weight in Newton and V bar is average stream velocity in the vertical in meters per second, and D is the depth of flow at the vertical in meters. Horizontal axis meters. These meters consist of a propeller mounted at the end of a horizontal shaft. These come in a wide variety of sizes with propeller diameters in the range 6 to 12 centimeter and can register velocities in the range of 0.15 to 4 meters per second. Nay, and watt type meters are typical instruments under this kind. These meters are fairly rugged and are not affected by oblique flows of as much as 15 degrees. The accuracy of the instrument is about 1% at the threshold value and is about 0.25% at the velocity of 0.3 meters per second and above. The current meter is so designed that its rotation speed varies linearly with the stream velocity v at the location of the instrument. A typical relationship is v is equals to a n sub a plus p, where v is the stream velocity of the instrument location in meters per second, and a is the revolutions per second of the meter, and A and B is the constants of the meter. Typical values of A and B for standard size 12.5 centimeter diameter price meter cup type is A is equals to 0.65 and B is equals to 0.03. Smaller meters of 5 centimeter diameter cup assembly called pygmy meters run faster and are useful in measuring small velocities. The values of the meter constants for them are of the order of A is equals to 0.30 and B is equals to 0.003. Further, each instrument has a threshold velocity below which equation 2 is not applicable. The instrument have a provision to count the number of revolutions in a known interval of time. This is usually accomplished by the making and breaking of an electric circuit either manually, either mechanically or electromagnetically at each revolution of the shaft. In older model instruments, the breaking of the circuit would be counted through an audible sharp signal or tick heard on a headphone. The revolutions per second is calculated by counting the number of such signals in a known interval of time, usually about 100 seconds. Present-day models employ electromagnetic counters with digital or analog displays.
Okay. So that's the propeller type current meter, the inertic type, and its sounding weight, you know, for getting discharge in large river. Okay, the propeller type cross section, no. This is the inertic type for smaller canals. Okay, the inertic type using a cable way. Okay, please continue.
Calibration. The relation between the stream velocity and revolutions per second of the meter as in equation 1 is called the calibration equation. The calibration equation is unique to each instrument and is determined by towing the instrument in a special tank. A towing tank is a long channel containing still water with arrangements for moving a carriage longitudinally over its surface at constant speed. The instrument is to be calibrated is mounted on the carriage with the rotating element immersed to a specified depth in the water body in the tank. The carriage is then towed at a predetermined constant speed v and the corresponding average value of revolutions per second and ns of the instrument determined. This experiment this experiment is repeated over the complete range of velocities and the fit
Mm,
linear relation in the form of equation 1 obtained. The instruments are designed for rugged use and hence the calibration once done lasts for quite some time. However, from the point of view of accuracy, it is advisable to check the instrument calibration once in a while and whenever there is a suspension that the instrument is damaged due to bad handling or accident.
Mahaba lang ang buhok niya eh. Mahaba ng lockdown eh. Mahaba na yung buhok.
Field use or field observation. To accurately determine the average velocity in a vertical section, one has to measure the velocity at a large number of points on the vertical. As it is time consuming, certain simplified procedures have been evolved. In a shallow stream of depth up to about 3 meters, the velocity measured at 0.6 times the depth of flow below the water surface is taken as the average velocity in the vertical. V bar is equals to V sub O times 6. This procedure is known as the single point observation method.
mm,
In moderately deep streams, the velocity is observed at 2 points. First one at 0.2 times the depth of flow below the free surface, V sub O multiplied by 2 and 2 at 0.8 times the depth of flow below the free surface, v sub O multiplied by 8. The average velocity is the vertical v is taken as v bar is equals to v sub O multiplied by 8 plus v sub O times 8 over all over 2. In rivers having flood flows, only the surface velocity v8 is measured within a depth of about 0.5 meter below the surface. The average velocity v is obtained by using a reduction factor k as v bar is equals to kvs. The value of k is obtained from observations at the lower stages and lie in the range of 0.85 to 0.95. Field measurements. 1. Wading. In small streams of shallow depth, the water meter is held at the requisite depth below the surface in a vertical by an observer who stands in the water. This is applicable only to small streams. Second is the cableway. In rivers flowing in narrow gorges in well-defined channels and stretched from bank to bank well above the flood level. A carriage moving over this cableway is used as the observation platform. Third is called bridges. While hydraulically not the best locations, are advantageous from the point of view of accessibility and transportation. Hence, railway and road bridges are frequently employed as gauging stations. The velocity requirement is performed on the downstream portion of the bridge to minimize the instrument damage due to drift and knock against the bridge piers. Fourth one is boats, most satisfactory for wide rivers to conduct current meter measurement. A cross-sectional line is marked by distinctive land markings and buoys. The position of the boat is determined by using two theodolites on the bank through an intersection method.
Okay. So going back in the conduct of field measurement, one is you do it by wading. Second, you can use cableway for big rivers. Then on top of bridges. And then if not, you use boats to measure the flow. No? And going back further, in field observation, the depth of current meter must be placed at 0.6 times the depth, this one. Okay. And the other one is you place the current meter at two depths, 0.2 and then 0.8 of the depth. Okay. In rivers having flood flows, the surface velocity is measured with a depth of about 0.5 meters below the surface. Okay? Yung may mga flood flow. So the average velocity is obtained by using a reduction factor K here. Measurement of velocity in discharge. Float method. Please
Float
proceed.
method. A floating object on the surface of a stream when timed can yield the surface velocity by the equation Vs is equals to S over T, where S is the distance traveled in time T. This method of measuring velocities, while primitive, still finds applications in special circumstances such as 1. A small stream in flood, and 2. Small stream with a rapidly changing water surface, and 3. Preliminary or exploratory surveys. While any floating object can be used, normally specially made leak-proof and easily identifiable floats are used A simple float moving on a stream surface is called surface float.
Mga kailangan
It
lang.
is easiest to use and the mean velocity is obtained by multiplying the observed surface velocity by a reduction coefficient as in equation 5. However, surface floats are affected by surface winds to get the
Mawawala.
average velocity in the vertical directly. The special floats in which part of the body is underwater is used. Rod float, in which a cylindrical rod is weighted so that it can float vertically, belongs to this category. In using floats to observe the stream velocity, a large number of easily identifiable floats are released at fairly uniform spacings on the width of the stream at an upstream section. Two sections on a fairly straight ridge are selected and the time to cross this ridge by each float is noted and the surface velocity calculated. Area velocity method. This method of discharge measurement consists essentially of measuring the area of cross-section of the river at a selected section called the gauging site, and measuring the velocity of flow through the cross-sectional area. The gauging site must be selected with care to assure that the stage discharge curve is reasonably constant over a long period of about a few years. Toward these, the following criteria are adopted. 1. The stream should be a well-defined cross-section which does not change in various seasons. 2. It should be easily accessible all through the year. 3. The site should be in a straight, stable reach. And 4. The gauging site should be free from backwater effects in the channel.
Okay, so that four criterion will give you the observations on how to select gauging site. O, yan dapat straight ang cross-section, no? Hindi curvature. Accessible all throughout the year. Should be straight and stable reach. Okay? At free from backwater effect, no? Yung kung may hindrance sa loob, biglang lalim ng tubig, actually it's not the actual depth because maybe there was a hindrance and causing backwater, no? Causing backwater. Okay. Please continue.
The area velocity method, commonly known as the current meter method, is based on determining the mean discharge using the velocity and cross-sectional area. If the mean stream flow velocity V is normal to the direction of flow and cross-sectional area A of the flow is known, the product of these variables determines discharge Q. That is, Q is equals to V multiplied by A. The hydrometric operation measures the stream depth and velocity at selected intervals across a stream either by wading, cableway, reach, or in a boat. The water depth and the positions across the stream are obtained using a rod for depth and a survey tape for distance. A current meter is used to measure the stream velocity at each selected interval. An ideal current meter should respond instantly and consistently to any changes in water velocity. Also, the meter should be durable, easily maintained, and simple to use. There are different types of current meter grouped into three major categories, which are the mechanical current meter, electromagnetic current meter, and the most recently introduced, which is the acoustic Doppler velocity meters.
Okay, procedures.
Procedures. First, select a site considering the criteria of a good gauging site. Second, determine the cross-section of the selected site to be considered by dividing it into large number of subsections by verticals. The following are some of the guidelines to select the number of segments. A. The segment width should not be greater than 1 over 15 to 1 over 20 of the width of the river. P. The discharge in each segment should be less than 10% of the total discharge. And C. The difference of velocities in adjacent segments should not be more than 20%. 3. Set the water level at 3 gauge heights and determine the velocity of each stage. Assemble the current meter to be used and determine the depth of water at the respective subsections. 5. The average velocity in these subsections are measured by current meters or floats using 0.6D method or 0.2D and 0.8D at respective 3 gauge heights. It is quite obvious that the accuracy of discharge estimation increases with the number of subsequent subsections used. However, the larger the number of segments, the larger is the effort, time, and expenditure involved. It should be noted that in natural rivers, the vertical for velocity measurement are not necessarily equally spaced. 5. Record the required observed data in prescribed form. 6. Calculate the discharge in each subsections at 3 gauge. 7. After completion, the field observation disassemble the current meter and should be properly kept in the instrument box.
Okay. So that is how it is being illustrated, no? So assuming this is the cross section, no? We've got to divide that into section as with width 1, 2, 3, etc. No? Just follow the criteria. Going back, the width should not be greater than 1 over 15 to 1 over 20 of the width of the river. So if the width is 20 meters, yung bawat section niya, dapat 1 over 20, mga 20 meters, 1 meter ang width. But you can also use 1 over 15 depending upon the engineer concerned, no? The discharge in each segment should not be less than 10% of the total discharge. Yeah. Okay? Please proceed.
Calculation of discharge. Figure 1.3 shows the cross-section of a river in which n-1 verticals are drawn. The velocity averaged over the vertical at each section is shown. Considering the total area to be divided into n1 segments, the total discharge is calculated by the method of midsections as follows. Q is equals to the summation of n minus 1, I is equals to 1, delta Qi, where delta Qi is the discharge in the ith segment, depth at the ith segment multiplied by 1 over 2 width to the left plus 1 over 2 width to the right multiplied by average velocity at the ith vertical. Delta Qi is equals to yi multiplied by yi over 2 plus yi plus I over 2 multiplied by bi, for I is equals to 2 to n minus 2.
Okay. For the first and last sections, please continue.
For the first and last sections, the segments are taken to have triangular areas and their area calculated as delta A sub 1 is equals to W bar sub 1 Y sub 1, where W bar sub 1 is equals to yi plus W sub 2 over 2 squared all over 2 W sub 1 and delta A sub n is equals to W bar n minus 1 Y sub n minus 1, where W bar sub n minus 1 is equals to w sub n plus w sub n minus 1 over 2 squared over 2w sub n to get the delta q sub I is equals to v bar sub 1 multiplied by delta a1, and delta q n minus 1 is equals to v bar n delta a n minus 1.
Okay. Example. Okay. The data.
The data pertaining to a stream gauging operation at the gauging site are given below.
So you are given there the distance from the left water edge, 0 meter, 1 meter, 3, 5, 7, 9, 11, and 12. The depth, you have 0, 1.1, 2, 2.5, 2, 1.71, then 0. You have the revolution of the current meter. You have 0, 39, 59, 112. That refers to the rotation, no? 90, 45, 30. Then the duration of observation, you have 100 seconds, 100, 150, 150, 100, 100, and 0. Okay? The rating equation of the current meter is B is equals to 0.51 ns plus 0.03 meter per second. You are asked to calculate the discharge of the stream. Okay? The calculations are performed in the tabular form for the first and last section. Mm. Papakibasa mo. Okay, please proceed.
The calculations are performed in a tabular form. For the first and last sections, average width W bar is equals to 1 plus 2 over 2 squared over 2 times 1, which is equals to 2 meters. For the rest, W bar is equals to 2 over 2 plus 2 over 2 is equals to 2 meters. Since the velocity is measured at 0.6 depth, the measured velocity is the average velocity at that vertical V bar.
Ito, yung lima rito.
Okay, and the calculation.
The calculation of discharge by the midsection method is shown in tabular form below. Distance from left water edge in meter: 0, 1, 3, 5, 7, 9, 11, 12. Average width in meters: 0, 2,
Ano, Chad?
3,
Pakita mo to. Ilabas mo.
11. Depth y in meters: 0, 1.1, 2.0, 2.5, 2.0, 1.7, 1.0, and 0. From the calculation, the total
So,
discharge Q is equals to 6.454 cubic meters per second.
so you have there the average width. You have uh, 2 meters, 11, 2 meters, 9 minus 7 is 2, 7 minus 5 is 2, no? This one. The depth of observation is like this. The velocity, 0.229, no? 0.229. Where did you get 0.229? From the formula. From the formula. The velocity is 0.51 n plus 0.003. No? Velocity is equals to 0.51 n plus 0.03 when is equals to revolution over time n. Okay, so if you try to get the first one, ilan yung revolution? You have 39, no? 39 B is equals to 0.51 times n revolution over time. 39 over 100 plus 0.03. So, pakisimplify mo nga. 0.59, 0.51 times 39 divided by 100. Ilan, Maika?
0.1989 po.
0.51 times 39 divided by 100. Ilan?
0.1989 po.
Plus 0.03. Mag-add ka ng 0.03. Ha?
0.2289.
Okay. So, ayan, andyan siya. Ano? So, the velocity was calculated using the formula. Okay? So, the velocity is 0.229. Now, discharge is velocity times the area. Okay? Okay? So, yun. Then, for the second one, you multiply 2 times 1.1 times 0.229. Ilan? 0.504. Is that correct?
0.5038 po.
5.
038.
Then, how about the next one? Average width times the depth will give you the area. Maki-multiply mo nga.
1.304 po.
Okay, times 0.229.
0.298.
0.2. Okay, we will analyze this further, no? Okay, please proceed again. The rating equation, sige,
The rating equation of the current meter is V is equals to 0.51 NB plus 0.03 meters per second. Calculate the discharge in the stream. The calculations are performed in a tabular form for the first and last sections. Average width W bar is equals to 1 plus 2 over 2 squared all over 2 times 1, which is equals to 2 meters. W bar is equals to 2 over 2 plus 2 over 2 is equals to 2 meters. Since the velocity is measured at 0.6 depth, the measured velocity is the average velocity at that vertical V bar.
okay. Yan, okay. Paki-review na lang niyo to. We will go back to this, no? We will check. I'm going to have it checked, no? Okay. Please proceed. Moving boat method.
Moving boat method, discharge measurement of large alluvial rivers by the standard current meter method is very time-consuming even when the flow is slow or moderate. When the river is in spate, it is almost impossible to use the standard current meter technique due to the difficulty of keeping the boat stationary on the fast-moving surface of the stream for observation purposes. It is in such circumstances that the newly developed moving boat techniques prove very helpful. In this method, a special propeller-type current meter which is free to move about a vertical axis is towed in a boat at a velocity v sub b at right angles to the stream flow. If the flow velocity is v sub f, the meter will align itself in the direction of the resultant velocity v sub r, making an angle theta with the direction of the boat. Further, the meter will register the velocity v sub r if v sub b is normal to v sub f. V sub b is equals to v sub r cosine theta and v sub f is equals to v sub r sine theta. In the time of transit between two verticals is delta t, then the width between the two verticals is w is equals to v sub b multiplied by delta t. The flow in the sub-area between two verticals I and I plus 1 where the depths are y sub 4 and y sub 4 plus 1 respectively, by assuming the current meter to measure the average velocity in the vertical is delta q sub I is equals to yi plus yi plus 1 over 2 multiplied by yi plus 1 v sub f.
So in this case, this is the only applicable for moving boat method, whereby you make use of alignment. So you just check. But for wading, you will no longer use this, no? But in case there is a correction because of the flow, uh, the formula is being applied in order to get the vertical velocity. Okay. Yeah. Okay.
Dilution
So let's now proceed to dilution technique. Maybe ask also another one to read this for us. Uh, volunteer? Maybe call in Akotina. Akotina. Akotina.
Sir,
Will you please read?
uh, hello, check.
Akotina.
Hello,
Oh,
check.
pakibasa
Sir,
mo nga.
okay na po.
Yeah.
Okay na po. Ay,
Delusion.
Dilution technique of stream flow measurement. The dilution method of flow measurement, also known as the chemical method, depends upon the continuity principle applied to a tracer, which is allowed to mix completely with the flow. Consider a
Sige,
tracer
sige muna. Teka
which
muna.
does
Teka
not
muna.
react.
Teka muna. Let's have 5 minutes break. Then we'll go back after 5 minutes, ha? 5 minutes
Okay
break
po, sir.
muna. Sige, sige. 5 minutes break.
Dilution technique or stream flow measurement. The dilution method of flow measurement, also known as the chemical method, depends upon the continuity principle applied to a tracer, which is allowed to mix completely with the flow. Consider a tracer which does not react with the fluid or boundary. Let CO be the small initial concentration of the tracer in the stream flow. At section 1, small quantity volume V1 of high concentration C1 of this tracer is added, figure 15. Let section 2 be sufficiently far away on the downstream of section 1 so that the tracer mixes thoroughly with the fluid due to turbulent mixing process while passing through the ridge. The concentration profile taken at section 2 is schematically shown in figure 15. The concentration of a base value of CO increases from time t1 to a peak value and gradually reaches the base value of CO at time t2. The stream flow is assumed to be ready.
Mm. So in this one, the sudden injection method, uh, you are given there the initial concentration, injection B1, and determine the percentage of concentration at the initial time when the substance was injected into the water, no? Please
Using the
continue.
dilution using the dilution principle, inject the tracer of concentration C1 at a constant rate of Qt at section 1. At section 2, the concentration gradually rises from the background value of CO at time t1 to a constant value C2, figure 16. At the steady state, the continuity equation for the tracer is this technique in which Q is estimated by knowing C1, C2, CO, and Q is known as constant rate injection method or plateau gauging. Q1 C1 plus Q CO equals to Q plus QT C2. Q is equals to QT multiply by C1 minus C2 over C2 minus C1 ay 0. C0. CO pala.
Okay. So you have the illustrated constant rate injection method at different section. Let's continue. Tracers.
Tracers. The tracer used should have ideally the following properties. It should not be absorbed by the sediment, channel boundary, and vegetation. It should not chemically react with any of the above surfaces and also should not be lost by evaporation. It should be non-toxic. Uh, Number three, it should be capable of being detected in a distinctive manner in small concentration. Number four, it should not be very expensive. The tracers used are of three main types. Number one, chemicals or common salt and sodium dischromate or typical. Number two, fluorescent dyes or rhodamine WT and sulforodamine B extra are typical. And number three, radioactive materials such as bromine 82, sodium 24, and iodine 132. Common salt can be detected with an error of plus minus 1% up to a concentration of 10 ppm.
Mm.
Use Use the dilution method has the major advantage that the discharge is estimated directly in an absolute way. It is a particularly attractive method for small turbulent streams, such as those on mountainous areas. With suitable, it can be used as an occasional method for checking the calibration, stage discharge curves, etc. obtained by other methods. Example 2. A 25 gram per liter solution of a fluorescent tracer was discharged into a stream at a constant rate of 10 cubic centimeter cubic centimeter 3 per second. The background concentration of the dye in the stream water was found to be zero. At a downstream section sufficiently far away, the dye was found to reach an equilibrium concentration of 5 parts per billion. Estimate the stream discharge. By equation 13, for the constant rate injection method, the formula Q equals QT multiplied by C1 minus C2 over C2 minus C0. Q1 equals 10 centimeter cube per second equals 10 times 10 raised to negative 6 cubic meter per second. C1 equals 0.25 C2 5 times 10 raised to negative 9 CO equals 0. Uh, Substitute Q equals 10 times 10 raised to negative 8 over 5 times 10 raised to negative 9 multiply by 0.025 minus 5 times 10 raised to negative 9. The final answer is 550 cubic meter per second.
Okay. Next method. Electromagnetic.
Electromagnetic method. The electromagnetic method is based on the Faraday's principle that an AMF is induced in the conductor, water in the present case, when it cuts a normal magnetic field. Large coils buried at the bottom of the channel carry a current I to produce a controlled vertical magnetic field. Figure 17. Electrodes provided at the sides of the channel section measure the small voltage produced due to flow of water in the channel.
Okay, that is how it is being illustrated. But then in our case, we seldom use it in the Philippines because of problems on maintenance, and at the same time it's very difficult to maintain, no? Aside from that, it is costly to operate. Okay, please continue.
It it has been found that the signal output E will be at the order of millivolts and is related to the discharge Q as Q equals K1 multiply ED over I plus K2 raised to N. Where D equals depth of flow, I current in the coil, and N K1 and K2 are system constant. The method of
The method,
the method involved sophisticated and expensive instrumentation and relations. The fact that kind of setup gives the situation where the cross-sectional properties can change with time due to width growth, sedimentation, etc. Another specific application is in tidal channel where the flow undergoes rapid changes both in magnitude as well as in direction. Present-day commercially available electromagnetic flow meters can measure the discharge to an accuracy of ±3%. The maximum channel width that can be accommodated being 100 meter. The minimum detectable velocity is 0.005 meter per second.
okay, the next one, ultrasonic method.
Ultrasonic method. This is essentially an area velocity method with the average velocity being measured by using ultrasonic signals. The method was first reported by Swingel 1995. Since then it has been perfected and complete systems are available commercially. Consider a channel carrying a flow with two
Transducers.
transducers A and B fixed at the same level, each above the bed and on either sides of the channel. Figure 18. These transducers can receive as well as send ultrasonic signals. Let A send an ultrasonic signal to
So
be
that is
received at
how it
B
is
after
being
an
illustrated.
elapsed time.
But these are already
Transducer
advanced,
send
no?
ultrasonic signals.
We will
Let
not
A send an ultrasonic signal to be
we will
received at
not
B after an
be using
elapsed
this in the
time. T1.
Philippines, at least to introduce that there is such a method of like this. Sige, please proceed. Ultrasonic flow meters.
Ul- Ultrasonic frequencies of the order of 500 kHz. Sophisticated electronics are needed to transmit, detect, and evaluate the mean velocity of flow along the path. In a given installation, calibration, usually performed by the current meter method, is needed to determine the system constantly. at many places and accuracies of above 2% for the single path method and 1% for the multipath method are reported. The systems are currently available for rivers up to 500-meter width.
Okay. The
The
specific.
specific the specific advantages of the ultrasonic system of river gauging are: number one, it is rapid and gives high accuracy. Number two is suitable for automatic recording of data. Number three, it can handle rapid changes in the magnitude and direction of flow, as in tidal rivers. And number four, the cost of installation is independent of the size of rivers. The accuracy of this method is limited by the factors that affect the signal velocity and averaging of flow velocity, such as unstable crossing section, double uh, fluctuating with growth, triple high loads of suspended solids, and 4, air entertainment, and 5, salinity and temperature changes.
Okay. Next, indirect methods.
Indirect methods under this category are included those methods which make use of the relationship between the flow discharge and the depth of specified location. The field measurement is restricted to the measurement of these depths only. Two broad classification of these indirect methods are: number one, flow measuring structures, and two, slope area methods. Flow measuring structures. The various flow measuring structures can be broadly considered under three categories. Number one, tin plate structures are usually made from a vertical set metal plate. The V-notch, rectangular full width and contractile notches are typical examples under this category. Number two, long base weirs, also known as broad crested weirs, are made of concrete of masonry and are used for large discharge value. Three flumes, Number three, flumes are made of concrete, masonry or metal sheets depending on their use and location. They depend primarily on the weight constriction to produce
Control section.
the control section.
Use
Use of structures. Use of structures like notches, weirs, flumes, and sluice gates for flow measurement in hydraulic laboratories is well known. These conventional structures are used in field conditions also, but their use is limited by the ranges of head, debris, or sediment load of the stream and the backwater effects produced by the installation. To overcome many of these limitations, a wide variety of flow measuring structures with specific advantages are in use.
Okay. Slope area method.
Slope area method, the resistance equation for uniform flow in an open channel, e.g., Manning's formula, can be used to relate the depths of either ends of a reach to the discharge. Figure 19 shows the longitudinal section of the flow in a river between two sections, 1 and 2. Knowing the water surface elevation at the two sections, it is required to estimate the discharge. Applying the energy equation to sections 1 and 2, C sub 1 plus Y sub 1 plus V squared sub 1 over 2G equals C sub 2 plus Y sub 2 plus velocity 2 sub 2 over 2G plus HL.
Okay, so that's the using the slope area method, no? But we will no longer, we will only be up to this, no? Okay, okay, okay. So we will now proceed to the next topic on hydrograph. But before so doing, break muna tayo. Break muna tayo. 5 minutes break. May we call on Lanzuela? Lanzuela, are you there?
Yes po.
Okay, will you please read? We are now on hydrograph, the last part.
Um, Definition of hydrograph. It is a detailed analysis of flood hydrograph concerned primarily with the three characteristics of stream flow. A graph showing change in the discharge of a river over a period of time. It is the response of a given catchment to a rainfall input, also known as storm hydrograph, flood hydrograph, or simply hydrograph.
Components.
Components of hydrograph, rising line, represented by AB joining point A, the starting points of inflection. It is influenced mainly by the character of the storm which caused the rise. Number two, crest segment is the points of inflection from the falling sides of the hydrograph commonly assumed to mark the time. Represented by variables BC between the 2 points of inflection with the peak P and between. Falling line, also known as the deflection curve. It represented by variable CD starting from the second point of inflection C. Other variables in hydrograph, T sub pk, it represent the time of peak from the starting point A. Lag time T sub L, the time interval from the center mass of rainfall to the center of mass of hydrograph. Q sub P is the peak discharge, and T sub B is the time based on the hydrograph. Phase of runoff. Overland flow, also known as a surface runoff. These are the waters that travels over the ground surface to the channel during a rain. Interflow, or a subsurface storm flow. Water that infiltrates the soil surface may move laterally through the upper soil until it enters a stream channel. Moves more slowly than the surface runoff. Groundwater flow, also called as base flow or weather flow. These are precipitation that percolate downward, or this is the movement of water that travels and seeps through soil and rock underground. It is part of stream flow that has infiltrated the ground, has entered the phreatic zone as a very low flow velocity. Division of total flow. Storm of direct runoff. consists of the surface runoff and substantial portion of interflow. Base flow consists of the groundwater flow. Factors affecting flood hydrograph. Climatic factor. Control the rising line and the recession line independent on the storm characteristic and being determined by catchment characteristic. Physiographic factors. Factors are the basin characteristic, shapes, size, slope, nature of the valley and elevation, drainage and density. From infiltration characteristic, we have land use and cover, soil type and geological condition, then lakes, swamps, and other storage. From channel characteristic, we have cross-section, roughness, storage capacity, and climate factor. We have storm characteristic,
Walang pataas.
we have precipitation intensity, duration, magnitude, movement of storm, and lastly, initial loss and evapotranspiration.
Kaya may ano yan. Alam mo, duty yan. Ang problema lang may kung ano. Dapat.
Shape of
Shape
the
of
base.
basin. It influences the time taken for water from the remote parts of the catchment to arrive the outlet. The occurrence of the peak and the shape of the hydrograph are being affected. Size. In a small catchment, the overland flow is predominant over the channel flow. Land use and the intensity of rainfall has an important role on the peak flood. In a large basin, this effect also suppressed as the channel flow phase is more predominant. Slope. It controls the velocity of flow in the channel. Stream channel slope has an effect on the recession line of the hydrograph.
Kita ko yung pataas. May dalawa yun. Lalo, yun yung dahil binibili niya. Para madali baligo.
Large streams
Large stream slopes gives rise to quicker depletion of storage and hence result in a steeper recession lines of hydrograph which cause a smaller time base. The steeper slope of the catchment result in a smaller enlarged peak discharge. Drainage density. It is the ratio of the total channel length of the total drainage area. Land use is the vegetation and forest increase the infiltration and storage capacities of the soil, thus causing the retardance to the overland flow. This result a reduced peak flow.
Pero makakuha ka ng ganyan na klase
The peak
ng
and the volume of the surface runoff are proportional to the intensity of rainfall. The duration of storm in a given intensity has also a direct proportional effect on the volume of runoff. The effect is reflected in the rising line and the peak flow. Direction of storm movement.
storage of water.
Storage of water. Number 1, surface storage. It includes both surface detention and channel storage. Number 2, interflow storage. 3, ground floor storage. Hydrograph base flow separation. The surface flow hydrograph is obtained from the total storm hydrograph by separating the quick response from flow from the slow response flow. Number 1 method I straight line method, separation of the base flow is achieved by joining with a straight line the beginning of the surface runoff to a point on the recession line representing the one of the direct runoff, where A is represent the beginning of the direct runoff and B as the end of the direct runoff. An, an empirical equation for the time interval n or days from the peak to the point B, where n is equal to 0.83 A raised to 0.3. A is represent the drainage area in inches, n represents the days, and the points A, B are joined by the straight line to demarcate the base flow and surface runoff. Simplest of all the three methods. The method next method is method 2. The base flow curve is extended prior to the commencement of surface runoff is extended till it intersects the ordinate drawn at the peak point.
Okay, so this is how it is being illustrated, no? This is picture. In method 1, all you've got to do is to separate base flow from runoff, connect just this one up to there. But the other one is pass a line and from the peak, then draw a perpendicular line there, then connect that to the one. So that's the second method. Hydrograph analysis. Please proceed.
Effective rainfall. For purpose of correlating DRH, direct runoff hydrograph, with the rainfall which produce the flow, the hydrograph of the rainfall is also prone by deducting the losses. The resulting hydrograph is known as the effective rainfall hydrograph or ERH. It is also known as hydrograph of rainfall excess or supra rainfall. Both DRH and ERH represent the same total quantity but in different units. ERH is usually in centimeter per hour plotted against the time. The area of ERH times catchment area is equal to the total volume of direct runoff.
Sample.
Example number 2. Rainfall of magnitude 3.8 centimeter and 2.8 centimeter occurring on the two consecutive 4 hours duration on catchment of area 27 kilometers squared produce the following hydrograph of flow at the outlet of the catchment. Estimate the excess and
P index. P index. P index. Hello?
time
Hello?
from of start of rainfall or H um negative 6, 0, 6, 12, 18, 24, 30, 36, 42, 48, 54, 60, and 66. Um, the value of observed flow or meter cube per second is 6, 5, 13, 26, 21, 16, 12, 9,
Wait.
7, 5, 5, 4.5, then 4.5.
Advance ka agad ang hanahanap. Magkano yung advance?
1,000 lang daw, boss, pang budget mo.
Ha?
1,000 lang daw. Sabi ko maya-maya lang nag-ano eh. Hindi ko.
Sige, please proceed.
It is seen that the storm hydrograph has a base flow component. Using the simple straight line method of base flow separation by this equation, n is equal to 0.83 times 27 raised to 0.2 is equal to 1.6 days or 38.5 hours. By inspection, DRH start at time is equal to 0 as the peak at T is equal to 12 hours and ends at the T is equal to 48 hours, which gives a value of N is equal to 48 minus 12 or equal to 36 hours. As N is equal to 36 hours appears to be the more satisfactory than N is equal to 38.5 hours. In the present case, DRH is assumed to exist from T is equal to 0 to 48 hours. A straight line base flow separation gives a constant value of 5 cubic meter per second for the base flow.
So you're given the
DRH or the area
the hydrograph. You are asked to calculate for the direct runoff. So the first thing that you will do is to separate the base flow from runoff. Base flow is the amount of water below. Runoff is the one above, no? So you are asked to calculate the area. So like for example, this one, from 0 to 6, get the area there. So the area is 6 times this height, no? You are given there, if you try to recall, the coordinates are the observed flow. You have 5, no? You have 5, then you have 13, next is 26, then you have 21, then 16, then 12, etc. So, in this case, this is 5. Then next is you have 13. 13. Okay? So 13 minus 5 is 8. So you have there 1/2 times 8. The next is 1/2 times 8 plus 21. You have 26. The height of this is 26. 26 minus 5 is 21. So you have again 1/2 times 8 plus 21. Then 1/2, 21 plus 16. Then hanggang doon sa dulo. Okay? So simplifying further, you have now 1,490 400 cubic meters. The total direct runoff due to the storm. So these are time, no? 6 hours. 6 hours, you convert that to 60 minutes per 1 hour, then 60 seconds per minute. So 6 times 6 times 6 will convert that to seconds. So nakapactor out siya. Nakapactor out siya. That's why computing for the area, you have this one. Okay? So the total direct runoff depth is equals runoff volume divided by catchment area. So 1.4904 times 10 to the power 6 divided by 27 times 10 to the power 6. So the rainfall excess is 0.0552 meters or 5.52 centimeter as the rainfall excess. The total rainfall will be 3.8 plus 2.8 equals 6.6 centimeter. The duration is 8 hours. So the Phi index is 6.6 minus 5.52 divided by 8. So you have 0.135 centimeter per hour. Okay, please proceed. Ako, Tina, Alansuela.
Unit hydrograph. The problem of predicting the flood hydrograph resulting from a known storm in a catchment has received considerable attention. A large number of methods are proposed to solve this problem, and of them probably the most popular and widely used method is the unit hydrograph method. This method was first suggested by Sherman in 1932 and has undergone many refinements since then. A unit hydrograph is defined as the hydrograph of direct runoff resulting from 1 unit depth or 1 centimeter of rainfall excess, occurring uniformly over the basin and at a uniform rate for a specified duration dH. Thus, one has a 6-hour unit hydrograph, then 12-hour unit hydrograph, etc. And in general, DH unit hydrograph applicable to a given catchment.
The definition,
The definition of a unit hydrograph implies the following. Unit hydrograph represents the lump response of the catchment to a unit rainfall excess of dH duration to produce a direct runoff hydrograph. It relates only the direct runoff to the rainfall excess. Since the volume of water contained in the unit hydrograph must be equal to the rainfall excess. As 1 centimeter depth of rainfall exists and considered the area of the unit hydrograph is equal to the volume given by 1 centimeter over the catchment.
Third.
Two, the rainfall is considered to have an average intensity of excess rainfall ER of 1 per day centimeter per hour for the duration of the storm. Next is the distribution of the storm and is considered to be uniform all over the catchment. Here are the duration of the rainfall exists in 6 hours. Area under of the hydrograph is equal to 12.92 times 10 raised to 6 cubic meter. Catchment area of the basin is equal to 1,292 kilometers squared. Two basic assumptions constitute the foundation for the unit hydrograph theory. One is the time invariance and two the linear response. Time invariance, the first basic assumption is that the direct run-off response to a given effective rainfall in a catchment is time invariant. This implies that the DRH for a given ER in a catchment is always the same irrespective of when it occurs. Linear response. Linear response means that if an input x sub 1, positive yan sir,
At time T1,
x sub 1 times t cos an
okay.
output of y sub 1 t and an input of x sub 2 times t cos an output y sub 2 times t, then an input of x sub 1 times t plus x sub 2 times t gives an output of y sub 1 times t plus y sub 2 times t. Consequently, if x sub 2 times t plus rx sub 1 times t, then y sub 2 times t plus ry sub 1 times t. If the rainfall exists in a duration d is r times the unit depth, the resulting DRH will have ordinates bearing ratio r to those of the corresponding d, then h unit hydrograph. Since the area of resulting DRH should increase by the ratio r, the base of DRH will be the same as that of the unit hydrograph. If two rainfall excess of d minus h duration, each occur consecutively, their combined effect is obtained by superposing the respective DRH, with due care being taken to account for the proper sequence of events. The method of superposition. Estimation of discharge unit using hydrograph. Example number 1. Given below are the ordinates of a 6-hour unit hydrograph for a catchment. Calculate the ordinates of the DRH due to the rainfall excess of 3.5 cm occurring in 6 hours. Time is 0, 3, 6, 9, 12, 15, 18, 24, and so on. UH or ordinate cubic meter per second is 0, 25, 50, 85, 25, 160, 185, and so on.
the resulting
The resulting DRS, as also the unit hydrograph, are shown in the figure. The desired ordinates of the DRH are obtained by multiplying the ordinates of the unit hydrograph by a factor of 3.5 as in the table of 6.2.
so you are given there. So you are time 0, second column, the ordinate is 0. Then time 3, ordinate 25, then you multiply it by how much is the rainfall? 3.5, no? So 3.5 times 25 will give you 87.5. Then 50 times 3.5, that will give you 175. Then 85 times 3.5 will give you 297.5. Then 125 times 3.5, you have 437.5. So forth and so on. No? So if you try to plot that, this is the resulting one. The hydrograph unit is this one. Then the 3.5 storm is now this one, no? Yan. Okay, this one. Ang second problem, two storm,
Two storm each of 6-hour duration and having rainfall excess values of 3.0 and 2.0 centimeter, respectively occur successively. The 2 centimeter ER rainfall fall, follow the 3 centimeter rain. The 6-hour unit hydrograph for the catchment is the same as given in example 6.3, calculating the resulting of DRH.
you read? So you are calculating now the by method of superposition. You have 0, 3, 6, 9, 12, 15, no? Then the ordinate, you have 25, 50, 85, 125, 160, etc. This is interpolated value. Then you have ordinate of the 3 centimeters storm. So you have 25 times 3, that will give you 75. 50 times 3, that will give you 150. 85 times 3, that will give you 255. 125 times 3, that will give you 375, and so forth and so on. While this one, it is lagged by 2 hours. So 3, 6. So nakalag na siya dyan. So where did you get 50? 25 times 2 will give you 50. 50 times 2 will give you 100. 85 times 2 will give you 170. Then 125 times 2, that will give you 250. Then you try to sum up. Okay? 25 and 75. Ordinate of the 5 centimeter storm, you have now 0. Then you have 75. Then you have 50. Then 255 and 50. That will give you 305. This times that 475, and so forth and so on. Okay? Please proceed.
Derivation of unit hydrograph. A number of isolated storm hydrograph by short of rainfall excess, each of approximately same duration, 0.90 to 1.1 dH, are selected from a study of the continuously gauged runoff of the stream. The area under each DRH is evaluated and the volume of the direct runoff obtained is divided by the catchment area to obtain the depth of ER. The ordinates of the various DRH are divided by the respective ER values to obtain the ordinates of the unit hydrograph. Flood hydrograph used in the analysis should be selected to meet the following desirable features with respect to the storm responsible for them. 1. The storm should be isolated storm occurring individually. Then the rainfall should be fairly uniform
During the duration and should cover the entire catchment area. Hello? Hello? Lanzuela? Hello? Can you hear me?
Yes, sir.
Okay. Please proceed. Please read. Hindi ka marinig.
Number 3, the duration of the rainfall should be 1/5 to 1/3 of the basin lag. Number 4, the rainfall excess of the selected storm should be high. A range of ER values of 1.0 to 2.0 centimeter is sometimes preferred.
Okay. Flood rational formula.
Flood
This is
rational formula.
Mm.
A flood is an unusually high stage in a river, normally the level at which the river overflows its banks and inundates the adjoining area. The damage caused by the floods, in terms of loss of life, property, and economic loss due to the disruption of economic activity, are all too well known. Thousands of errors of roofs are spent every year in flood control and flood forecasting. The hydrograph of extreme flood and stage corresponding to the flood peak provide valuable data for purpose of hydrologic design. Further of the various characteristics of the flood hydrograph, probably the most important and widely used parameter is the flood peak. At a given location in a stream, flood peak vary from year to year, and their magnitude constitutes a hydrologic series which enable one to assign the frequency to a given flood peak value. In the design of particularly all hydraulic structures, the peak flow that can be expected with a assigned frequency, say 1 in 100 years, is primarily important to the adequate proportion the structure to accommodate its effect. The design of bridges, culvert, waterways, and spillway for dams and estimation of score at a hydraulic structure are some examples wherein flood peak values are required.
flood rational formula. Maybe call on another one. Uh, Ivalya? Ibalya?
Sir,
Will you please read?
flood's rational formula. To estimate the magnitude of a flood peak, following alternative methods are available. 1.
To
Rational
estimate the
method.
magnitude of a flood peak, the following alternative method
2. Empirical method. 3. Only hydrograph technique. 4. Flood frequency studies. The use of particular method depends upon the desired objective, 2. The available data, and 3. The importance of the project. Further, the rational formula is only applicable to small size, 50 kilometers squared catchments, and the unit hydrograph method is normally restricted to moderate size catchments with areas less than 5,000 kilometers squared. Rational method. Consider a rainfall of uniform intensity and very long duration occurring over a basin. The runoff rate gradually increases from zero to a constant value, as indicated in Figure 7.1. The runoff increases as more and more flow from remote areas of the catchment reach the outlet, designating the time taken for a drop of water from the farthest part of the catchment to reach the outlet as Tc equals to time of concentration. It is obvious that if the rainfall continues beyond Tc, the runoff will be constant, and at the peak value of the runoff is given by Q P equals to CAI for PTC. Rational method, where C is equals to coefficient of runoff equals to runoff rainfall, A is equals to area of the catchment, and I equals to intensity of rainfall. This is the basic equation of the rational method using the commonly used units. Equation 7.1 is written for field application as QV equals to 1 over 3.6 C I P times A. QP equals to peak discharge meter cube per second. C equals to coefficient of runoff. ICP, the mean intensity of precipitation for a duration equal to a TC and an exceedance probability P. A equals to drainage area in kilometers squared. The use of this method to compute QP requires three parameters: I, I, and IC, IK, and IKP, and C.
The mean intensity of precipitation in millimeter per hour for a duration equal to T sub C, I sub C, and an exceedance probability P. And then A, the drainage area in square kilometer. The use of this method to compute QP requires parameter I, IC and times P and capital letter C. Let's proceed.
Rational
Rational.
method. Time of concentration, PE, PC. There are a number of empirical equations available for the estimation of the time of concentration. Two of these are described below. US practice for small drainage basins, the time of concentration is assigned to be equal to the lag time of the peak flow, thus TC equals to TP of equation 6.10 equals to CL times LLCU over square root of S raised to E, where TC equals to time of concentration in hours, C, CA, and S have the same meaning as in equation 6.10 of chapter 6. Kirchhoff's equation, 1940, this is the popularly used formula relating the time of concentration of the length of travel and slope of the catchments as Tc equals to 0.01947, L raised to 0.77, S 0.36, 385, Tc equals to time of concentration minutes. L, maximum length of travel of water in meters, and slope of the catchment equals to HL, in which H equals the difference in elevation between the most remote point on the catchment and the outlet. For ECU, equation 7.4 is sometimes written as this equals to 0.01947 K raised to negative 0.77, where K equals to square root of L over H. Rainfall intensity. The rainfall intensity corresponding to a duration Tc and the desired probability of exceedance P, return period T equals to 1 over P, is found from the rainfall frequency duration relationship for the given catchment area. This will usually be a relationship of the form of equation 2.15. IKP equals to KT over TC plus A, in which the coefficients K, A, and X and N are specific to a given area. Table 2.8 could be used to estimate these coefficients to a specific catchment. In USA, the peak discharges for purposes of urban area drainage are calculated by using P equals 0.05 to 0.1. The recommended frequencies for various types of structures used in watershed development projects in India are as below. SI number 1. Type of structure, storage and diversion dams having permanent spillways. Return period 50 to 100 years. 2. Earth dams having natural spillways 25 to 50 years. 3. Stock water dams 25 years. 4. Small permanent masonry and vegetated waterways is 10 to 15 years. 5. Terrace outlets and vegetated waterways 10 years. 6. Field diversions 15 years.
Runoff coefficient.
Runoff coefficient. The coefficient C represents the integrated effect of the catchment losses and hence depends upon the nature of the surface. Surface slope and rainfall intensity. The effect of rainfall intensity is not considered in the available tables of value of C. Some typical values of C are indicated in Table 7.1 A and B. Equation 7.2 assumes a homogeneous catchment surface if, however, the catchment is non-homogeneous but can be divided into distinct sub-areas, each having a different runoff coefficient. Then the runoff from each sub-area is calculated separately and, and merged in proper time sequence. Sometimes a non-homogeneous catchment may have component sub-areas distributed in such complex manner that distinct subzones cannot be separated. In such cases, a weighted equivalent runoff coefficient as below is used. C equals to summation of C1 A over A.
The values of C for the rational formula. It's there, no? Then you are given also the values of C in the rational formula for watershed with agricultural forested land covers. All you've got to do is just to select the characteristic and then use that in the formula to fill in C. Okay? These are examples. Okay? Okay, next, last part. SES curve number. Please read. Ibalya?
Sir, SCS curve number method. The SCS curve number method is a simple, widely used and efficient method for determining the approximate amount of runoff from a rainfall even in a particular area. Although the method is designed for a single storm event, it can be used to find average annual runoff values. The stat requirements for this method are very low: rainfall amount and curve number. The curve number is based on the area's hydrologic soil group, land use, treatment, and hydrology condition, the two former being of greatest importance. The general equation for the SCS curve number method is as follows: Q equals to P minus IA over 2 of I raised to 2 over P minus IA plus S. Then where Q equals to runoff, P equals to rainfall, S equals to potential maximum retention after runoff begins, IA equals to initial obstructions. The initial equation is based on trends observed in data from collected sites. Therefore, it is an empirical equation instead of a physically based equation. After further empirical evaluation of the trends in the database, the initial abstractions IA could be defined as a percentage of S. With this assumption, the equation could be written in a more simplified form with only three variables. The parameter Cn is a transformation of S, and it is used to make interpolating, averaging, and weighing operations from linear. With the following chart, the amount of runoff can be found if the rainfall amount in inches and curve number is known. There are two advantages of using LTHIA over a manual method. One, the availability of the data. LTHIA provides the rainfall data for any area in the United States. Two, LTHIA completes this calculation for every rainfall event for 30 years and then reports the average annual runoff value. Note: curve number, the parameter S representing the potential maximum position depends upon the soil vegetation, land use complex of the catchment and also upon the sediment soil moisture condition in the catchment just prior to the buon.
Where are you now?
Sa curve number, sir, malabon kaya hindi ko po nababasa.
The parameter representing the potential maximum depends upon the soil, vegetation, land use, complex, and catchment, and also upon the antecedent and moisture condition in the catchment just prior to mahihirapan din ako magbasa. Anyway, that's only for notation, no? So this is the curve number that we are referring to. Okay? The curve that you will use. And these are the characteristics where you will use the curve number for hydrologic soil group. No? Like for example, it is agricultural, no? A is 64, B is 75, verb number is 82, letter D is 85. For commercial, these are the values, no? Yan. 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 Nakasobra. Balik natin. Last part.
Yes, part po.
Sige pa. Okay. So, in such a case, that will be all as to hydrology. Okay. Now, our last meeting will be next week, which will be at the same time the schedule of final exam. No? Final exam. As I have said, there will be two parts in the final examination, part 1 and then part 2. The first part will be good for 1.5 hours. The second part will be good for 1.5 hours. Okay? The second part will start from evapotranspiration. Okay? Evapotranspiration. Feynman's equation, doon ang maumpisa ng kwan. While the first part will be precipitation and the rest part of abstraction from precipitation. So, be ready for examination next meeting, which will be our last meeting also. And I hope you bring in one paper with you, with your name, so that that will be the one that will be submitted and posted on the blackboard. Okay, please study very well, and I hope if you have some question, you can wrote it out, and then we may schedule another meeting, maybe Saturday in the afternoon, if you want, to review some of the possible problems that will be given. But your examination is definitely Sunday from 8 to 11, 2 parts. Okay, any question? Any question? Hello?
None po.
Hello?
None, sir.
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 Okay,
Sir.
so
Ako, sir.
mag-schedule tayong kuhan, maybe for 1 hour, Saturday afternoon, around 3 o'clock, just only to refresh you with some examination questions. And after that, examination will be Sunday from 8 to 11. Okay? Any more question?
None, sir.
Okay? Kung wala na,
Wala po.
thank you very much for attending. See you this coming Sunday and Saturday around 3 p.m. 3 or 4
Thank you,
p.m.
sir.
Okay. Thank you.
Thank you, sir.
Yes, sir.
Salamat din po, sir.
Thank you, sir.
Ingat kayo po.
Sir.
Okay.
Bye, sir.
Bye, sir.
Bye po, sir.
Bye, sir.
Bye, sir.
Enrique present.